Yeah, so this is Tuesday, the 28th. So just doing a quick loop problem. And, right, I've always got this little Liotte list here, and I'm seeing that trigs come before exponentials. So I want to make u my sine of x. And then, of course, du is cos of x, right? And dv is e to the minus x dx. So v is integrating is minus e to the minus x. I did that one real quick, right? Just but I can see the u sub is a -1. I know I'm going to need a -1 out front, right? So I get uv, so minus e to the minus x sine of x minus the integral of v du. So v is already negative. So I get an e to the minus x cos of x dx. Oops. And you could see the cosine is going to bounce back and forth, right? Sine, cosine. With or without a negative, we have to just be careful about that. So I'm kind of doing the same problem again, right? But I've got to redo my lists, and now u is cos of x, du is negative sine of x dx, and v is the same, right? So I'm just going to try and save a little space here by using this little symbol from the original problem until I'm ready to put that original problem back in. So I get uv no, there's no dx there, sorry, minus the integral of v du. And you can see here, oh, I got a triple negative here, right? Du is negative, v is negative. So I've got my e to the minus x sine x dx. And you can see that's my original problem, right? That's the original problem. So I want to now realize that I want to write that original problem here. And then my solution. And notice that this term, whatever it is, remember it's an area, right, or a volume or whatever. So so I can add it to the other. I can add it to both sides, right? So I'm adding this integral to both sides, and now I'm going to have two of those on the left. Yeah, and I can definitely factor out a negative e to the negative x. And I get sine x plus cos x. Yeah. Yeah. And now I divide by 2.
Yeah.
Yeah. So final answer. Right, and then plus the constant c. And it doesn't matter if we pretended we divided it by 2 or not, because just it's some new constant now. So that's the thing is you're going to just kind of realize that the original problem is back in there.
Yeah.
And it had better not cancel out. It's funny, you'll see if I picked the wrong value of u, meaning I switched my Liotte list, when I go to bring that integral piece back to the beginning, they cancel out completely, and I end up getting 0 equals 0. So that's a good mistake to make, to pick the wrong value of u in one of these loop problems and see what happens. What else? Anything else you want me to do? Nice. So we've got a couple of things done today. We got a real fun piece to do today. I know it's hard to believe, but again, I'm a nerd. But we've talked about a few things already. Brian, I did the same deal I always do. You're going to take a final exam. If it's better than your current test, it'll replace it. Okay? Just like I did last semester. So we've done a few things already, and I'm jumping around a little bit just because I'm ADD. But we've talked about a few things, and we'll get to Paul's note list soon. But he's got you saying, "Hey, try this when this happens. Try this when this happens." Right? So be looking at that. So when I introduce the test, you're familiar with it already, right? Read that, do some of his example problems. On your test, I will say to you, use an integral test, use a ratio test, okay? So I'm just trying, because I know it's too much, just trying to take some of that difficult process away. And then all you have to do is show me you can do the calculus, right? But if you can't do the calculus, right, that's my worry. If you can't do the calculus, who cares what test you're using, right? So far we've done the integral test. We've done the ratio test. I'll talk more about that today. And we've done power series, creation, right? And radius of convergence. The radius of convergence for a power series will always come from a ratio test. But I will tell you, find the radius of convergence using a ratio test, okay? And for the radius, there's three possibilities. Right? There's three possibilities. Either the radius could be 0, okay? The radius is 0. The radius is infinite. Or the radius is some fixed number, like 1, right? We've seen it to be 1, and we're talking about less than, absolute value of the radius is less than 1. Now, when we do a ratio test, we do a limit. So what do you think is going on with the limit in each of these cases? Well, when I get an actual number, I'm going to get an actual limit, right? When I actually get, I didn't want to do that. It's too late. So when I actually get a number, the limit is going to be some number, right? When I get a radius of 0, well, when the radius is infinite, the limit is going to go to infinity, right? Is that true? Don't tell me. I have to look. Sorry. $5.95. Okay, sorry. Yeah, yeah, of course it makes sense. So the limit here is 0, right? So when I do that ratio test, I do a limit. If I get a limit of 0, it means that there is no radius. It's only going to work at the center. The book will do a lot of shifts of functions. I keep everything centered at 0. Okay, like you saw me do a couple of functions where it started wrapping on the other function. It was always around the origin. I could shift to another point, right, by just changing the function, right? Like f of x equals x, or f of x equals x minus 3. Now the center is at 3, right? So if you're interested at a certain value, you can just take your whole series and shift it. I don't bother doing that. So just so you know, when you're looking at problems, if you see a shift, right, x plus or minus something, they're just moving the center. So let's go over all of this morning, and then we're going to add something new today. I was going to give a quiz today, but there's not much point if I'm just going to give more zeros. So if other students don't show up, I'll just wait till tomorrow for the quiz. Okay? I'm not doing it to make grades worse. I'm trying to help the grades a little bit by saying, hey, I'll put something on the quiz today that was on the test. If not identical, something very close, right? All right, let's do an integral test first, a couple of integral tests. Well, what does it say about my function, or about my my series? I need the terms to be positive and decreasing, right? So let's say a sub n is n squared over n cubed plus 1. This one turns out to be divergent, and so when it is divergent, we want to be thinking about, so this is in red is f of x equals x squared over x cubed plus 1, right? We want to be thinking about drawing our areas above. So if we can show that the integral is divergent, right? If we can show that red area cannot be calculated, then for sure the blue area cannot be calculated, right? So I just know the answer. That's why I'm telling you this one is going to end up being divergent, but yeah. If you do a comparison test, right? If you do a comparison test, what's the mother function of downstairs? Right? Downstairs, the mother function is n, right? This really, in the long run, kind of behaves like n squared over n cubed, which is 1 over n. And that is divergent, right? So we're thinking this thing really is going to behave like something divergent with a comparison test. So, but we want to do an integral test, but we have to make sure two things. Terms are positive, that's pretty obvious, right? Because n's are 1, 2, 3, 4, or right? Or even 0 if I can, but I don't care about a finite number of terms not being positive. And so on this particular one, we are starting at 0. What happens at 0? When I do the n equals 0 to infinity of n squared over n cubed plus 1, what's the very first term is 0, right? So I don't care about a finite number of terms not being positive. What's my very next term? One half? Yep, and then the very next one, and when it's, I get 2, it's what? 4/9, right? So I want to make sure this thing is decreasing after a finite number of terms. And the easiest way to do that, of course, is to find the derivative, right? So in order to use the integral test, I need all but a finite number of terms to be positive, and all but a finite number of terms, I need the function to eventually just be decreasing. So clearly positive, right? So how do I show that it's decreasing? I'm going to do a derivative. So quotient rule, so you should be doing this with me. I take the top function and its derivative, and then the bottom function and its derivative, and I use a loop with like a letter Q, right, to show that I need this product minus this product, right? Hey, morning. So y prime, and Teddy, this is the first thing I'm doing, but I'm recording, okay? So 2x times x cubed plus 1 minus x squared times 3x squared, all over the original function, the downstairs squared, right? I try to factor if I can, but in this case it just looks like a mess here. But anyway, what do I get? I get 2x to the fourth plus 2x minus 3x to the fourth so it looks like I get 2x minus x to the fourth and I can factor out an x there. And clearly x's are positive, right? Because we're talking about the integral. Really, I'd say I had originally set it up from 0 to infinity, but let me chop off that first term so I know I don't have terms of 0, I have positive terms. And I just have to think about when is it possible that 2 minus x cubed is less than 0, because that's what I want, right? And when does that happen? Yeah, when it's greater than the cube root of 2. And you can kind of see, you know, what's going on with this. It's a cubic. It's doing something like this. So it's hitting that. It's becoming negative after cube root of 2, right? What number is cube root of 2? About 1.26. So meaning I failed to show my derivative was negative until after the third term. But that's fine, as long as it's decreasing after the third term, that's fine. I don't care about a finite number of terms, right? I can calculate those areas, right? Looking at that box, right? I can calculate the first two areas easily of the blue areas, right? So then all I really care about is after, actually this is 1, so all I care about is after 2. So I know for sure for n is 2, right? I have no problem using the integral test. So that's what I'm going to do. I mean, I can do after 1, but there's no need, right? So 2 to infinity of, what did I have? X squared over x cubed plus 1 dx. So I already know I need a limit. As soon as I see that improper piece, I want to write this thing as a limit. Then I have to think about my integration methods. I have to think about integration methods. I see a couple of you using this function almost like it's a Simpsons rule problem. I can't use this function, I have to integrate, right? Does that make sense what I'm saying? I see the possibility of an improper. If I'm in doubt, I draw the graph, right? But when I have an integral going to infinity, I know it's improper. So I write it as a limit. Then I have to integrate. I have to go back to my chapter 5 list. Do you recognize it? Is it a power rule? Is it a sub, U sub, 3, 4 levels of U sub? Is it by parts? Is it partial fractions? I have to go through that list. This one looks like it could be partial fractions, but I can see if I let U be downstairs, right? If I let U be the downstairs, du is 3x squared dx, and I can get that. So I've got the limit as a goes to infinity of the integral from 2 to a of, let's see, I need a 3 upstairs, so I'm going to multiply by 1/3, right? Divide by 1/3. Is that okay? I multiplied upstairs by 3. I have to cancel it by dividing by 3. So this is the limit as a goes to infinity of 1/3 of the ln of the absolute value of x cubed plus 1, evaluated at a and at 2. Is this okay? Everybody following? Go ahead. Yeah. When I'm doing that. Remember, I'm getting an infinite area or volume. I want to see if it actually adds up to some number, right? So then I have to evaluate. Yeah. So now where am I evaluating at? I'm evaluating at a, but there I have to take a limit, and then I'm evaluating at 2, and I don't have to take a limit, right? So the limit as a goes to infinity of 1/3 of the ln of a cubed plus 1. Obviously, I don't need the absolute value at this point, right? Because I know I'm bigger than 2 even. Minus 1/3 of the ln of, what is that, 9? So, yeah. 2 cubed, right?
Yeah, but I'm saying.
Oh, yeah, 3 squared, and I can, yeah. But I don't care so much about that piece. I'm worried about the first piece where I take the limit. And I already know what ln of a cubed plus 1 looks like. It looks like ln. And so where is that piece going when I take that limit? Infinity. Of course, infinity plus or minus a finite number is still infinity. Yeah. So diverges. Say it again.
You were saying the sum was bigger than this, you were taking
Yes, yeah.
the sum also.
That's right. So I had decided, this was the original problem, right? And I want my terms to be positive and to be descending, right? To be getting smaller, so with a limit to 0. So, and so my first term, right? And instead of starting, so my first term, what was my first term? I actually did it 0, so it's not really contributing to the sum at all there, right? My next term, when n was 1, I got a 1/2, right? Okay, but so they are decreasing after that, but I took my derivative, right? And I saw that I really didn't get my decreasing terms until x was bigger than 1. So, in order to use the integral test, I need things to be decreasing. That's happening when n is 2 and on. Right, so I don't care about the finite number of terms. Yeah. Let's do another one. So there's an integral test with a u sub. This is an integral test with another thing happening here. So a sub n equals 3 over n squared minus 3n plus 2. So let's do a couple of things with this. First of all, we want to think about, can we use the integral test, right? And then does it converge or diverge? This one, I don't know if you can see it already, but if I use that mother function idea, what's the mother function downstairs? Yeah, n squared. So I'm really comparing this to a 3 over n squared, which we know converges, right? So we're thinking it converges. Let's start with the graph. I'm using Noah's. Hopefully you've got one of these saved already. If you don't, type it. I want you to be able to type it, right? So we start with that list of n, right? So you're on Desmos, you can start typing that first piece there. I'm changing this to 3 over n squared minus 3n plus 2. And then I need that last piece to plot my points. Say again? Oh, thank you. There we go. Thank you. So you can see here, there's an issue at 1 and 2, right? It's not even plotting those for me. What's going on when n is 1 and n is 2? Well, when n is 1, I get a 0 downstairs, right? When n is 2, what do I get downstairs? 0. So I can't use those first two elements, right? I can probably change my list to start at 3. Will it let me do it? Oh, get rid of the comma. Yeah. Yeah, it didn't, did it? Oh, it did, yeah. So we're thinking positive for everything, right? I probably should look at that downstairs piece about, well, I know it's a quadratic opening up, right? Can you see it? That downstairs is a quadratic opening up. So after a certain point, right, after that second root, I know I definitely have positives. So the positive piece is not a problem. Is it decreasing? Well, that's really easy to tell as well, right? Again, from that downstairs piece, but certainly a derivative is going to be the key that you can use this. How can we take that derivative? This is x squared minus 3x plus 2, right? Or 3 times x squared minus 3x plus 2 to the negative 1, right? So the derivative is pretty damn quick. It's negative 3 times x squared minus 3x plus 2 to the negative 2 times the derivative of the inside, which is what? 2x minus 3? So the question is where is that critical value of the first derivative? What is it, 3/2? Yes? So if x is bigger than 3/2, that negative 3 controls the sign of the derivative, right? If x is bigger than 3/2, the 2x minus 3 is positive, yes? Yep. The downstairs is for sure positive. I'm squaring it. So I know that the derivative is negative after x is 3/2. Since a sub n is positive for n greater than or equal to 3, and a sub n is decreasing for n bigger than 2, right? 3/2 is 1.5, so certainly the next integer I can be talking about is 2. The integral test can be used. Which is nice because that's everything we did in chapter 5. So we want to see if it converges, right? We want to go from 3 to infinity of 3 over x squared minus 3x plus 2 dx. Well, look at that downstairs. What happens? Yeah. So I can do a limit as a goes to infinity of the integral from 3 to a, and I can factor that downstairs. What is it? Minus 2 minus 1? Is that right?
Yeah.
It sucks, right? The problems turn into other problems, and you're like, oh shit, now I got to start. Oops, like recording. Now I got to start a new problem again, right? But it is what it is. You got to deal with it. So let's work on the side for our partial fractions. You should be writing. You should be racing me. We like it when it's nice and simple like this. Anybody, we get 3 and -3 for our, well, it depends on how you wrote your
Yeah.
3 and -3, right? Whichever one's first, doesn't matter, depends on how you did it. I'll give everybody else a second here. How we do there? We there? Yes? Nice. Teddy? Yeah, nice. Good. So now we're looking at, and so I called my original integral star, right here, called the original integral star. I'm working on this piece of it, right? I still need to limit as a goes to infinity of two integrals now, right? The integral of 3 over x minus 2 dx plus the integral, or minus the integral of 3 over x minus 1. Right, my integral is going from 3 to infinity, right? Well, it's pretty clear that I'm going to get, that I just have an ln, a shifted ln, right? Is that true? Everybody, you can see a 1 over x there, but it's shifted to the right by 2 and then shifted to the right by 1. So I know it's still an ln problem, right? So I can factor out that 3, and I could just be looking at the ln of x minus 2. I don't need absolute value minus the ln of x minus 1. Because remember, my x's are starting at 3. Now, look at what happens when I plug in my infinite limit here. I get an infinity minus infinity, right? Both of these are ln's clearly going to infinity, right? But infinity minus infinity is an indeterminate form. There are different sizes of infinity. Sometimes infinity minus infinity is 0. Sometimes it's not. So I have to be thinking about how I can turn this into a single fraction. And that's pretty easy, especially if you had me for pre-cal, because I tortured you with it. Right? This is the ln of x minus 2 over x minus 1. Remember all those properties of logarithms in pre-cal? Pretty much have to know them the rest of your mathematical life. Well, now I can evaluate, right? Evaluate it at a and evaluate at 3. When I evaluate at a, I definitely need the limit. So what do I get? 1 ln of 1/2, right? Oh, sorry. Evaluate at a first. So I get a minus 2 over a minus 1 minus at 3, which is ln of 1/2. Is that agreeable? When I plug into 3 to x minus 2, I get a 1. When I plug into 3 to the x minus 1, I get a 2. So what happens with this ln, if you remember, ln's continuous, I can move that limit inside. Minus ln of 1/2 is the same as plus ln of 2. It doesn't matter that you do that part. But if you remember about the continuous functions, limits can move inside of the function. So, and there I'm at L'Hopital's rule, right? So what do I get? I get ln of 1, right? So converges. So on the test, I'll say, and this is one problem on your final test, verify that the integral test can be used, right? And then show that the following converges. Using the integral test. How are we doing? Okay? Nice. So we're talking about the radius of convergence for a series and what happens when I get a power series. What happens when I get a different limit from that ratio test? There's only three possibilities. I get a radius of 0, I get an infinite radius, or I get some finite radius, right? So let's look at each of those, what happens, and then we'll go back to our power series from yesterday. So we're talking about power series radius of convergence. So let's look at the first example. So here's one where it only converges at its center, and the book will say center because if you can see when x is 0, well, how about this? This thing looks like some kind of polynomial, whether it's an even power or an odd power, but it definitely goes through 0, 0, right? It goes through 0, 0. Like if I plug in x is 0, yeah,
But
or n is 0. Sorry.
no, it's zero back further upon x is 0.
Yes. So this is the easier way for me to say it. When I say centered at 0, or a radius only at the center, you could see me do something like this.
Okay.
Yeah, so you see it's just a shift from the origin to some shift left or right of the, yes, at x equals 0, yeah. So the book will talk about at the center. I'm always talking about at 0 because I'm ripping out all the problems that have a shift in it, because it's no different. If I can do it when the notation is a little bit easier, then I'm okay with that. Okay, so we're going to find this radius of convergence, and we're going to always do the ratio test on this. And when on your exam, I'll tell you, all right, find the radius of convergence of this power series using the ratio test. Okay. So, but I want to see what happens. This one supposedly will only have a radius of the center, meaning size 0. It will only converge when x is 0. So here we go. We want to look at the limit, is n goes to infinity of n plus 1 factorial times x to the n plus 1 all over n factorial times x to the n. Remember what I'm doing. I'm going one step further for the numerator, right? One n bigger, so n plus 1, and then the original for the denominator. Even though this absolute value does nothing, we want to think about this radius as the radius of a circle. So if I'm at the center of the circle, I'm looking right on the axis both directions. So that's what the absolute value is telling me. I want to peel off that first term of the n plus 1 factorial. So I'm going to take off an n plus 1, and then there's still an n factorial left. I'm going to take the x to the n and then times another x. That's x to the n plus 1. Everybody okay there? Make sure you're looking at that. Make sure you're comfortable with that. Yeah. Sometimes you might even need to peel off two terms. So if I had like an n plus 1 factorial, that would be an n plus 1 times an n minus 1 factorial. Sometimes you'll have to even do that. So some things cancel here, which is nice, right? The n factorials cancel. The x to the n's cancel. And it looks like I get the limit as n goes to infinity of n plus 1 times x. But where the hell does n plus 1 go to? Right? It goes to infinity. And I need some radius right? I need a radius bigger than that. Does it happen? Say it again? No. So can this happen? No, right? And so that means it's only going to converge at the origin. That's the only place it will converge. So when I get a limit of infinity and I need my radius to be bigger than that, we know it can't happen. So we just flip it over and say, hey, it's got to be 0. And of course, the sum of n equals 0 to infinity, 0 to 0, what was it, n factorial x to the n? I get 0 factorial 0 to the 0, so I get 0. I get the sum of 0. That's all, and that converges there. That's it. Every other term is gone, right? It is 1, but 0 factorial. Yeah. 0 factorial is 1. 0 to the 0 is 1. Yes. So it converges to 1. Remember, my first term of my power series, x to the 0, we're always saying that that's 1. So whatever the coefficients turn out to be. Yeah, right? Yeah, it's funny. All right, let's look at the next one. The sum of n equals 0 to infinity of negative 1 to the n, x to the 2n, all over 2 to the 2n, times n factorial raised to the second power. And you'll see some of the ones that we're going to be creating pretty soon, starting today, are as crazy as this. This one, I say, has a radius, an infinite radius, converges for all x's. So, for example, what did we see when the radius? When I got the radius is bigger than infinite, it's false, right?
Yeah.
Can't happen. So that says there's no radius of 0. If I get the radius is bigger than 0, when is that true? Always, right? So that's going to be my infinite radius. So I'm looking for these things for my limits, right? So let's do our ratio test here. The limit as n goes to infinity of -1 to the m plus 1. Kind of silly for me to even put that in there because I know the absolute value is going to kill it anyway, but that's fine. 2 to the x to the 2 times n plus 1. 2 to the 2 times n plus 1. m plus 1 factorial squared. Yuck. Horrible, right? Well, what's nice about the absolute value, it's going to kill these, so I can stop thinking about those, right? And then I want to expand these exponents here that have some work to do. So I've got an x to the 2n times x squared. Hopefully you can see that without too much trouble. So just trying to expand, trying to be patient, right? Maybe double checking myself, right? 2 times quantity n plus 1, that's 2n plus 2. Yes, okay, I got that. So now a bunch of things will cancel here, which is nice. Oops. Yeah, that's right. Nope, that's not right. So where's this limit going? Well, remember the x is a fixed value, right? So it might as well be a constant. But n is not fixed, right? So n downstairs is going to infinity. So this particular limit is going to 0. And I must get a radius that's bigger than that. So any radius will work. And so here's my point with this radius. If you remember what I want to call like wrapping like I have some function and I put in these terms and they start to touch the function at certain intervals, right? You remember the one we saw yesterday, everything was a radius of 1. It didn't connect to the graph past plus or minus 1. This one is going to connect to the graph the whole way. It's just going to be almost an identical match to the graph if I use all my terms. So when you're creating power series, practice getting the radius of convergence, okay? So listen to me again. When you're doing section 8.6 and you find your power series and you check the answer and it's right, then get the radius of convergence with this ratio test. Yeah. Nice. Let's do a quick, easy power series, and then one that you can expect to see on the test. Okay, and then we'll take a break. So let's find a power series. Is this okay? Everybody all right? Teddy, don't let me go too fast if you need to go back. You okay? So let's find a power series. I guess we can find the radius of convergence as well. So I'm going to give you f of x equals x cubed over 3 minus x squared. Remember where I'm trying to plug in. I'm trying to plug into 1 over 1 minus that piece. I'm trying to plug into that piece, right? And I'm also trying to plug into the radius of convergence. So I want to manipulate this function to look like this green box, right? I can get a 1 upstairs easily by just factoring out that x cubed. I can get the 1 in the bottom left of the denominator by dividing everything by 3. And then I can clearly see I can just wrap that bottom right addend in parens, and that's really hinting at me what I want here, right? I want this piece to be this piece, to be this piece, to be this piece. So f of x is equal to x cubed over 3. Right, this is I'm just repeating this, sorry. But I want it in the series. I want it to be x cubed over 3 times the series of n equals 0 to infinity of x squared over 3 to the n. Oh, I forgot to the n here, right? Sorry. So this is the thing I want on my formula sheet, right? I want this kind of little map of knowing I'm going to try and turn my rational function into this form. And then once I can find what goes in those parens, I can put it in the parens everywhere here in my little kind of cheat sheet. It's important to realize here that my sum is dependent upon what? My sum is dependent upon what? What is the variable controlling the sigma notation? N. So that x is basically can be treated like a constant. It can be moved in or out of the sum. The sum is not dependent upon that, right? So I'm really looking at, the sum of n equals 0 to infinity of let me move this guy in, x cubed over 3 times an x to the 2n over, 3 to the n, right? So I like coefficient first, right? So what do I have? I have 1 over 3 to the n plus 1 times x to the 2n plus 3. The book will usually write the coefficients as not denominator pieces, right? So like that. Let's do a little we'll do some rapping here today and see what happens. Let me not go too fast. Does anybody? Let me give you guys a couple minutes. Yeah. Is that enough or?
Yeah.
Yeah. Let's write out some terms here. Don't let me go too fast. No, don't let me go too fast. Yep, but don't, make sure you're, how do I close this stupid thing? Why can't I close it? Oh, maybe I just, there we go. I want to write out a few terms here. Help me, please. When n is 0, so this is the easiest way to do it, okay? Is I go 1/3 to the 0 plus 1 plus x to the 2 times 0 plus 3. That's, times, right? That's my first term. And then second term is 1/3 squared x to the 2 times 2 plus 3. Oh, 2 times 1, sorry. Right? Starting at 1, then plus 1/3 squared. At this point, I don't have to look at anything, right? X to the 2 times 2 plus 3 plus 1/3 to the 3rd x to the 2 times 3 plus 3. So once I get started with it, it's pretty quick. But now I want to clean them up, right? What did I do? Sorry. Yep. Yep. So I get 1/3 x cubed plus 1/9 x to the 5th. Okay, now I know it's 357, right? Plus 1/27 to the 7th. I go one more, plus 181 x to the 9th. Say again?
You got 1 over 8.
Thank you. Plus dot, dot, dot. Enough to do a for wrap and see what's going on. So I want to plot the original function, right? And then I want to plot the sum of the first terms, first 2 terms, first 3 terms, first 4 terms, and see how it's wrapping on the function, how it's representing the function. So go into Desmos. Graphing my original function, y equals, I forget already, x cubed. Yeah, over 3 minus x squared, right? Nice, pretty funky. But I remember I have powers of 1/3 and then odd powers of x, right? So for just the first one, 1/3 times x. And look how perfect it is at the origin. They cross, right? At the origin, they cross. So it's a perfect representation of the other function at that one point. Then what do I get? 1/9. Is it starting with 1/3 x cubed? Oh, sorry. Oh, 3, 5. Yeah, sorry. Yeah. Yeah, it's going to be even better. But don't get the 1/9 in there. Sorry. Right? Oh, yeah. Really good. In fact, so good up to what, 0.25? Or 0.2? Is that cut into 5 pieces? 1, 2, 3. Yeah, right? So then adding the next term plus 1/9, x to the 5th, right? What do you think? Good up to 0.75? Pretty close, right? Oh, not 0.75. Where is it? Yeah, 0.75. Pretty damn close, even at 0.75. Plus 1 over 27, x to the 7th. Whoa, look at this sucker. Where is it? Almost perfect too. Almost all the way to 1. I'm tempted to say that this has got a radius bigger than 1.
Yeah, because another is extra number 3.
Right. So I'm tempted to say that this radius is bigger than 1, but I'm doubting that it's bigger than what? 4, 3, 2. Yeah, but look at it. Look at that. The red, right? Yeah. So I'm thinking maybe 2, but let me go one more, okay? Plus 1 over 81 times x to the 9th.
But we know from like the previous version that it's 3.
Yep, exactly. So, but I'm thinking it's bigger than 1. But from what I'm seeing, I'm thinking it's bigger than 1. You agree? Because it looks like it's now good past 1, past right of 1 and left of -1, right? Which is my middle dash mark, right? From 0 to 2. There's the 1, right? It looks like it's good past 1. Is everyone agreeing with me? You see what I'm saying? Yeah? All right, so let's find the radius of convergence, right? Let's do it the long way with our ratio test. So we want to find the radius of convergence here. I'll write it over on a new page. Sorry. So I'm looking at the limit as n goes to infinity of 1/3 to the n plus 2, x to the 2 times n plus 1, all plus 3, all divided by that original piece. Well, there's no n. I don't know if you're there yet. There's no n in my limit. So I know I'm going to get a 1/3 x squared in absolute value. If I get a limit of 0 or a limit of infinite, I know, right, an infinite limit, I know my radius. So in this case, we know it. We got to be making sure, because we're talking about a power series, right? That it's less than 1. And of course, you see I get what? X squared is less than 3, or x is less than square root of 3. So not quite 2. I was thinking 2, at least when I was looking at it, right? Not quite. And you can actually see where this, so if I look at that original f of x, I've got what, x cubed over 3 minus x squared. Can you see the square root of 3 being an issue down there, right, in the denominator? It's kind of where my asymptotes are, right? So I'm not going to, this thing is never going to break outside of the asymptotes. Now, what did I plug in? I plugged in x squared over 3. Remember this little thing I had here? Where was my little cheater table for the test, right? There's my little cheater table for the test. And remember what I plugged in, x squared over 3. Look at it. Look at it, x squared over 3. Do you see how quick that's giving me the radius of convergence? All right, cool. So, let's just do one more, a power function representation where I have to either do a derivative or an integral. And there's one in there where you have to do it twice. Typically, I'll put one like that on the test, so make sure you do that one. I'll do one like that later this week or next week. Good, let's do Let's do 14, x squared inverse tan of x cubed. So this is 8.614. Yeah. I want a power series to represent this. And then we're going to find the radius of convergence. Can you picture arctan? Right, it's doing something like this. Okay. So there's no issue of an asymptote here blocking off the radius, right? Pretty smooth curve after a while, correct? So we're thinking on these continuous curves that the radius of convergence will be infinite. The discontinuous curves should be obvious. It's not. I can't cross a vertical asymptote, right? But let's see what we can do here. Now, the issue is probably this. The issue is probably that. I think I can get a nice version of arctan and then just multiply it by x squared to get my original, right? So, but this doesn't look anything like what I want, right? Remember what I want? I want 1 over 1 minus something, right? Go ahead, I'm listening. Yes, the derivative, because derivative of arctan is 1 over 1 plus the inside squared, right? Yeah, so watch what I'm going to do. I think I can just work on the arctan piece.
Okay.
Yeah, so I'm going to say y is arctan of x cubed. And then what am I going to do? I'm going to take a derivative. So y prime is 3x squared over 1 plus x to the 6th. Right, you with me there? Yep. So that is starting to look a little bit more like what I want. In fact, it looks a lot like what I want. That's a 3x squared, right, times 1 over 1 minus a negative x to the 6th. Right, remember, that's what I'm looking for. So it looks like, what do I get? I get 3x squared times the sum of n equals 0 to infinity of negative x to the 6th to the n. Yeah, exactly. Yeah, yeah, exactly. So I can pull all of this into my series, and I want to, knowing that I have to integrate, right? But and this is important, when I'm integrating, I don't care about the constants, the coefficients, right? When I'm integrating, the coefficients go for the ride. When I'm differentiating, the coefficients go for the ride. So I know I need to get back to y, I need to integrate here. And so what do I get? The sum of n equals 0 to infinity of negative 1 to the n times a 3. I have to add 1 to my exponent and divide by that new exponent. Not much. Remember, I said I want to be careful. Once I create a new series, I want to be careful about having nonsense terms in it, and I do not. You agree? My first term is a x to the third, right? Next term is what? X to the ninth, then 15th, right? So no zero terms, no, so looking pretty good.
Somehow there was an integer that was negative 1/2.
Exactly, right. So I can look at my original now. Remember, now I have, remember this is now what? X squared y, right? I figured out my series for arctan. So now my series for f of x is going to be x squared times this series. So it's just going to change my x exponent by 2 more, right? It's going to be a little painful, but I want to write out a couple of terms here because I want to see what happens when I try and represent the original function. I need a little help, please. Looks like my first term is x to the 5th. Agreed? Anyone agreed? Yep. Yep. My next term is negative 1/3 x to the 11th. Help me, please. Anybody agree? Nice. Plus 1/5 x to the 17th. I think I can see the pattern here without doing much more plug in, right? I know x to the 5th, x to the 11th, x to the 17th, it's got to be x to the 23rd next. 1/1, 1/3, 1/5, it should be 1/7 next, but a negative, right? Yep. That's good enough for me. So what should we do? Desmos first or radius of convergence first? Convergence? Oh, I'm sorry. I just can't hear. I'm old. Yeah. Good. Let's take a look at this radius of convergence here for this guy. And how are we going to do it? What test are we going to use? Ratio test. So we want to look and see if this limit, and I'm telling you I'm going to get a limit of 0 out of this, which means any radius will work, any value of x will work. I'm crossing out these negatives because I don't care. I know the absolute value is going to kill them, right? Crossing out the 3's, obviously, and then the rest I'm going to try and simplify as quickly as I can. 6n plus 11. They don't. They don't get an infinite radius. I don't know why. Yeah. Yeah, so I've got 6n plus 6 plus 5, that's 6n plus 11. And then 6n plus 6 plus 3, that's 6n plus 9. Yeah, I'm just foiling it, right? And then keep change flip. So the 6n plus 3 goes to the numerator, and x to the 6n plus 5 goes there. Yeah. But I'm not getting what I want for some reason. Maybe I'm wrong on this one. So I have a 6n plus 3 over 6n plus 9. Where does that go for the limit? That goes to 1, right? And then I'm going to have x to the 6 left over here. So I don't get a 0 radius. I thought I would. Sorry, a 0 limit.
I was doing the Desmos and it falls off.
It does fall off. Yeah, yeah. I'm gonna trust the ratio test before I trust my instinct. Yeah, so I just get x to the 6 is less than 1. So the radius is 1. All right, let's look at the Desmos anyway. Don't let me go too fast, though.
I think the x squared.
Yeah, oh, the outside influence of it, yeah.
Like arcana extra or like
Yeah. Yeah. Cool, so let's see what happens. And to Desmos, I've got my original function of x squared arctan x cubed, right? Oop. Oh, yeah, yeah. Look what it's doing to arctan. Right? Remember arctan was, right, just a nice simple curve, definitely the limit of, as x goes to infinity, goes to pi over 2. And this x squared out front is just crushing it, right? Making it explode. All right, let's see what a couple of my terms are here. Y equals, what, x to the 5th was my first? Wow. It already looks like a cubic to begin with, right? Or an odd, definitely an odd polynomial. And you can see I'm just adding a bunch of odd polynomials here. So now minus 1/3, right? Times x to the 11th. Pretty cool. Plus 1/5 x to the 17th. Jeez.
I like how it looks like the every minus.
Yeah, it's pretty sick looking. It's like whoosha. Yeah, right. Minus 1/7 x to the 23rd. Yeah, it's so desperately trying to get past 1, but it can't. Pretty cool, huh? Now, what are we saying? If you're going to use this machine to calculate, right? If you're going to use the machine to calculate something really close to 0, it's pretty much perfect. And what's even better, how easy is it for you to calculate with arctan compared to with x to the 5th or x to the 11th or x to the 17th? Well, you don't have a calculator, how you do an arctan of, right? So, but the polynomials we could do easily, right? Yeah, I know. All right, cool. Let's take a little break. Let's come back at 10 of 10, okay?